Okay, so yes, the title of this talk is Sample Complexity of Tree Search Configuration, Cutting Planes, and Beyond. So an important property of those algorithms that are typically used in practice is broad applicability, the ability to solve problems across diverse domains. And I think this is maybe best illustrated by integer programming solvers, which are, of course, one of the most popular tools for solving combinatorial and oftentimes non-convex problems, and have a staggering array of applications in computer science, operations research, and beyond, such as routing, manufacturing, scheduling, planning, finance, and many others. However, these very broadly applicable algorithms can sometimes have unsatisfactory default out-of-the-box performance with slow runtime, poor solution quality, among other downfalls. And one of the challenges is that these very broadly applicable algorithms like integer programming solvers have a ton of tunable parameters. So for example, Cplex comes with a 170-page manual describing 172 different tunable parameters, and tuning these parameters by hand is just a notoriously slow, tedious, and error-prone process. And this raises the question, what's the best configuration of my algorithm for the particular application domain at hand? Whatever configuration is best for solving the routing problems that a shipping company has to solve day after day is probably not particularly well suited for solving the scheduling problems that an airline has to solve day after day. Well, in practice, we often have ample data about the particular application domain in which we'll be using this algorithm, data that we could potentially harness in order to learn the best configuration for the application domain. So for example, a shipping company will have access to all of the routing integer programs it has to solve day after day. A biolab will have access to all of the clustering integer programs it has to solve week after week. And airline will have access to all of the scheduling integer programs it has to solve on a day-to-day basis. So over the past 2 decades or so, there's been a lot of interest in using machine learning and data-driven techniques for these kinds of discrete optimization problems, especially from an empirical perspective. So here's just a small sample of the papers that have looked into this problem. And in this talk, I'm going to focus more on the theoretical end of this topic, of which there's been surprisingly a little research so far. And in particular, I'm going to describe guarantees, provable guarantees for integer programming parameter optimization. And I'm going to focus on cutting plane selection and describe some of the first provable guarantees for algorithm configuration in the context of cut selection. Okay, so with that introduction, I'm going to start off with an overview of our results and the integer programming framework in which we're going to be working. So I'm sure this is all familiar to everyone here, but just to make sure we're on the same page, our goal in integer programming is going to be to find a vector z that maximizes some linear objective c dot z, subject to some linear constraints, az is less than or equal to b, and subject to the constraint that the entries of z are integral. And as I mentioned, this integer programming has just a ton of applications throughout science. Okay, and we're going to be wanting to configure our integer programming solver so it has optimized performance for our particular application domain. And how do we model our application domain? Well, we're going to assume that these integer programs are drawn from some unknown application-specific distribution, D. So you could think of D, for example, as a distribution over the routing integer programs that this shipping company has to solve day after day. And this modeling assumption has been widely made in prior research from an applied perspective. So here's just a couple of papers that made this assumption, as well as theoretical research on algorithm configuration. Okay, and now what would this automated data-driven approach to configuration look like? So first we would fix some parameterized integer programming solver like Cplex or Gurobi. Then we would receive a training set of typical integer programs sampled from this unknown application-specific distribution. So this could be, say, all of the routing integer programs that the shipping company had to solve over the course of a year. Now we're going to perform some optimizations, and we're going to find a parameter setting which has good average empirical performance over this training set. And by performance, I mean it builds small search trees, it has low runtime, and so on. And in particular in this talk, we're going to be focusing on building small search trees. And now there are a couple of key questions that we need to answer about this procedure. First, how do we find parameter settings which have good average empirical performance over the training set? And this algorithmic question has been of significant interest, especially in the applied perspective over the past few years. And second, which is going to be the focus of this talk, is no matter how we optimize these parameters using your favorite parameter optimization algorithm from this applied research, can we guarantee that this parameter setting we come up with will have good future performance on future integer programs from the same application, but which aren't already in our training set? Looks like I've got a question. Oh, okay. Great. And a bit more formally, can we guarantee that the expected utility of this parameter setting we come up with is high? We know it has good average empirical performance over a training set, but will it also have good expected utility or expected performance over our distribution? So basic statistics tells us that as the size of our training set grows, the average utility should converge to expected utility as long as this algorithm we're trying to configure isn't totally crazy. So, but from a more quantitative perspective, the key question we want to answer in this talk is how many samples do we need, or how large should the training set be to ensure that for any choice of these parameter settings, the difference between the average empirical performance of that parameter setting over the training set and its expected performance or expected utility is at most epsilon for some epsilon. And just to illustrate this concept with a picture, you could imagine we're tuning the number of samples in the training set along the x-axis. And I'm plotting here the gray dotted line is the average empirical utility of some parameter setting as a function of the number of samples. And it will have a lot of variance, especially when the number of samples is small, but that variance should get smaller and smaller as the number of samples grows. And let's say that this blue line is the expected utility of this parameter setting. So that's not a function of the number of samples in the training set. And here I have epsilon bars around the expected utility of our parameter setting. And we want to know how many samples do I need to ensure that the average empirical utility, or the gray dotted line, is within epsilon of expected utility, or the blue line. And just to make this concrete, maybe epsilon is like 0.1, and maybe we need like 400 samples to ensure that this convergence property holds. And I want to emphasize that by answering this type of question, we thereby provide guarantees that apply no matter how the parameters are configured. No matter what algorithm you use to configure your parameters, optimally or suboptimally, manually or automatedly, you can be guaranteed that however well that parameter setting performed over the training set will be indicative of how well it will perform in the future. Or in other words, so long as you have good average empirical utility, you'll also have good expected utility. And what are like the key challenges that we face in providing these types of provable guarantees for algorithm configuration? And it's really that an algorithm's performance is just a notoriously volatile function of its parameters. So you can imagine we're tuning some parameter rho along the horizontal axis, and we're plotting some measure of performance like runtime or solution quality as a function of the parameter. And these functions are just notoriously volatile with many jump discontinuities. And intuitively, this is because in these combinatorial domains, if you just tweak an algorithm's parameters by a little bit, you can cause a cascade of changes in the algorithm's behavior, which causes these jumps in its performance. So overall, there's just a very complex connection between the algorithm's parameters and its performance. And this is really unlike those functions that we really understand well from a theoretical perspective in machine learning, where there's typically a fairly straightforward connection between a function's parameters and its value on any input. We don't really have this predictable structure in algorithm configuration. So we have to understand what structure is there, which will allow us to provide these types of guarantees. Okay, so we're going to be working in the framework of branch and bound, which is the most widely used algorithm for solving integer programs, and is used under the hood by Cplex and Gurobi. So now I'm just going to give a brief overview of branch and bound, which I'm sure will be familiar to many of you. So in branch and bound, we start off with an integer program like this one at the top here. Our goal is to maximize this linear objective subject to the single linear constraint, and subject to the entries of this vector z are binary. And the first thing we do is we solve the linear programming relaxation of this integer program, and we store it in the root of this tree that we're going to be building. And it's the objective value of that LP relaxation is 140. Then we branch on a variable. Say we branch on the first variable z1. And this means that in the left child of the root, we solve the LP relaxation of the original integer program, but with the additional constraint that z1 equals 0. And in the right child, we solve the LP relaxation of the original IP, but with the additional constraint that z1 equals 1. We continue doing this. We choose a node, we branch on a variable, this time z6. And in the leftmost child here now, we're solving the LP relaxation of the original IP, but with the additional constraints that z1 equals 1 and z6 equals 1. So we keep doing this, choose a node, branch on a variable. And at this point, something to note is that in this leftmost child, the optimal solution to the LP relaxation is actually integral. So it's a feasible solution to our original IP. And this means that we can prune this node, which means that we're not going to continue exploring this branch of the tree. And we can do this because there's no way that we're going to find a better integral solution by continuing to branch on variables. And in fact, we can also prune these other two nodes because the LP objective value in the leftmost node, 133, is larger than the LP objective function of the other nodes, 116, 118. Our goal is maximization, so we know we're not going to find a better integral solution than this leftmost child along either of these two branches. Okay, so we keep doing this, choose a node, branch on a variable. And at this point, we can actually stop. We can prune these last two nodes because, again, their LP objective values, 120, 120, are smaller than 133. So now we can terminate, branch and bound is done, and we can guarantee that we found the optimal integral solution. And in the worst case, there are 7 variables. We could have built a tree of size 2 to the 7, but we were smart about how we built this tree, and we were able to build a small tree. And in this talk, I'm going to be focusing on building small search trees. First of all, because that allows for low memory usage. And second of all, kind of in a hand-wavy way, squinting in your eyes, all else being equal, if the trees are small, then you'll have a faster runtime. Okay, and this talk is about cutting planes. So what is a cutting plane? So a cutting plane is an additional constraint that you add to your integer program, which first of all separates the LP optimal solution from your polytope. So say this is your feasible region, this gray line, and these are the integral points inside of your feasible region. This black dotted line would be the cutting plane. And here's the LP optimal solution. It's cutting away the LP optimal solution from the rest of the polytope. And the intuition is that this will tighten the LP relaxation, which will allow you to prune nodes sooner in your search tree. And second of all, cutting planes should never separate away any integer point, because then you'd be in danger of separating away the optimal integral point. So modern integer programming solvers add cutting planes throughout the branch and bound tree, and we call the resulting algorithm branch and cut. And as Corney-Jules writes, these cutting planes are in large part responsible for breakthrough speedups of these modern integer programming solvers. So what are the key challenges in applying cutting planes? Well, first of all, there are many different cutting planes that you could apply. For example, SchwartzGommery cuts, cover cut, clique cuts. These are families of cuts that are maybe even infinite or even exponentially large. So it's challenging to figure out which cut should I actually apply at any given point of the tree. So I'm going to be talking about several different ways of several different types of sample complexity guarantees we can provide for cutting plane selection. And our first set of results will apply to this classic family of SchwartzGommery cuts. So what is a SchwartzGommery cut? So this CG cut is parameterized by some vector u of dimension m, where m is the number of constraints that we have. And the way that the CG cut works is you dot u with every column of your matrix A and take the floor. So this creates a new vector of length and the number of variables. So that's the left-hand side of the constraints. You also dot the vector u with your right-hand side of the constraint B. You take the floor, and this creates a new constant, which is the right-hand side of your constraints. So this is the CG cut. And you can see there are infinitely many of these CG cuts for every parameter setting u. And so some important properties of these CG cuts is that they're valid. They're never going to separate away an integral point. And they can be chosen such that the CG cut will separate away that LP optimum. And one of the key challenges that we face in providing any kind of provable guarantees for applying these CG cuts is informally small changes to this parameter setting u can cause exponential jumps in the size of the tree that branch and bound builds. And I'm just going to illustrate this on one slide. Where is this sensitivity coming from? Okay, so let's start off with this illustration. So Z1 and Z2 are two variables in our integer program. And these gray dots represent the integral lattice. And let's say that this blue region is the feasible region of our integer program. So you can see that it's an infeasible integer program because there are no integer points inside of our feasible region. And it turns out that just vanilla branch and bound will build a tree of exponential size before it realizes that this integer program is infeasible. However, if you set your CG cut parameters just right, then your CG cut will look something like this gray dotted line here. So it will totally cut away the feasible region of this integer program, which will mean that branch and cut will terminate immediately. However, if your CG cut parameters don't fall within this region, then your CG cut will look something like this gray dotted line here. And it won't remove any of the feasible region at all, in which case, again, branch and cut is going to build this tree of exponential size. You haven't removed any of the feasible region. So basically, there's this hyperplane in the CG cut parameters, where on one side of the hyperplane, branch and cut builds a constant size tree, and the other side it builds an exponential size tree. It's a very sensitive function. Nonetheless, we are still able to provide positive provable guarantees. And in particular, we prove the following generalization bound or sample complexity bound, which tells us for any choice of these CG cut parameters u, what's the difference between branch and cut's average empirical performance on the training set after applying that cut defined by u and its expected performance on this unknown distribution? Or again, in other words, it's future performance on future integer programs from the same application. And again, you can think of performance, for example, as tree size. And I want to mention that for simplicity, I'm framing this question in terms of just applying a single CG cut at the root, but we also generalize to applying sequences and waves and cuts with only a polynomial increase in the resulting bound. And I want to make this point again, which is that so long as this difference is small for any choice of these parameters u, you can be guaranteed that no matter how you choose u, using your favorite optimization technique, you can be guaranteed that strong average empirical performance over the training set will be indicative of strong future performance. And in particular, we prove this generalization bound of h, where h is an upper bound on this performance function over the square root of your distribution, times the square root of m, where m is the number of constraints, times log the maximum norm of the matrices defining your LP, your integer programs over the square root of your distribution, plus the maximum norm of the b constraint vectors over the square root of your distribution, plus n, where n is the number of variables, divided by n, where n is the size of your training set. So the key takeaway here is that this difference between average empirical performance and expected performance will go to 0 as the number of training instances grows. We tell you exactly how quickly it will go to 0. So long as you have enough training instances, you can be guaranteed that good average empirical performance will be indicative of good future performance. Now, let me just give you an idea of kind of how do we go about proving these types of guarantees. Well, the key idea in the proof is that this tree size, this notion of tree size, we can prove it's a piecewise constant function of these tunable parameters u as a function of this. When you fix the integer program, the tree size is a piecewise constant function of u. And more specifically, there's a finite number of hyperplanes partitioning the u parameter space into regions such that in any one region, the branch and cut tree is fixed, no matter what parameter setting you use in that region. So just to illustrate this, imagine we're plotting our u parameters along the x and y axis. We're looking at tree size as a function of these parameters, and we can see that this function is piecewise constant. So intuitively, what this is saying is that despite there being an infinite number of parameter settings, there's only a finite number which have different algorithmic behavior. And so intuitively, we can take a union bound over all of these regions in order to get our sample complexity bound. And more formally, we use this learning theoretic tool called pseudodimension. And now, why does this piecewise structure actually hold? Kind of, what is the intuition behind this piecewise structure? So now, let me just remind you of what these CG cuts look like. They're parameters by these vectors u, and we take the inner product between u and our constraint matrix A. We take the floor, and we take the inner product of u and the right-hand side of the constraints, and that's our new, this creates our new constraint. Now for any u, parameters u, and column of our matrix A, the ith component of our new constraint u transpose A is going to be contained between the negative norm of AI and the norm of AI. And that's because u is contained between 0 and 1. And now for every integer whose magnitude is less than the norm of AI, we know that the ith component of our new constraint is going to equal that integer so long as ki is at most the inner product of u and ai, and it's at and this in turn is at most ki plus 1. And if you look at this formula, we're defining essentially the norm of A plus n many half spaces. And that's why this norm of A plus n is showing up in the number of hyperplanes that we get in this lemma. And in any region defined by the intersection of these half spaces, every single component of this constraint vector is fixed. We can kind of give a similar argument for the right-hand side of the constraints. And this is how we show that there are these hyperplanes, splitting the parameter space into regions, such that these constraints are fixed. Okay, so that's just the proof idea in one slide. And this is how we get our guarantees for these SchwartzGommery cuts. Now I'm going to describe another technique for using machine learning for cut selection, which is using what I'll call score-based cut selection policies. So in practice, cuts are often selected using these score-based cut selection policies, which work as follows. First, you compile this large set of separating cuts, and then you branch on the cut that maximizes some real valued score. And there are a lot of different options of what could you use for this score function, and little known about which to use when. So to give some examples, one common scoring rule is efficacy, which is the distance between the cut, say this black dotted line, and the LP optimal solution, which says this black dot. Another common one is parallelism, which is the angle between the objective vector and the cut's normal. So this black dotted line, let's say this black dotted line is the cut and the blue line is representing the objective vector. So this would have good cut parallelism because these are parallel lines. And in contrast, this black dotted line here on the right would have worse parallelism because the lines are no longer parallel. So in this work, rather than try to characterize the optimal scoring rule, we say, given these scoring rules, how can we provide guarantees for learning a mixture of scoring rules, mu1 score 1 plus ... mu d score d? And we're certainly not the first to consider convex combinations of scoring rules. For example, the leading open source solver Skip uses this affine combination of these scoring rules with hard-coded weights for 4 commonly used scoring rules. And again, we see that this branch and cut tree size is just a very sensitive function of this parameter mu. So in these plots, I'm plotting mu along the horizontal axis for 2 scoring rules. So we're looking at the mixture of 2 scoring rules, mu times score 1 plus 1 minus mu times score 2 for 2 commonly used scoring rules. And we're plotting tree size as a function of this scoring rule in Skip. And you can see that for these 2 different integer programs, this is just a very volatile function with many jumps. But nonetheless, despite this sensitivity, we're still able to provide this generalization bound, which tells us for any mu, what's the difference between that cut selection policy's average performance over the training set and its expected or future performance on our application domain. And again, performance you can think of as tree size. And again, just to drive this point home, so long as this difference is small, you can be guaranteed that no matter how you choose mu, good average empirical performance will be good, indicative of good future performance. And in this case, we get this generalization bound of H, which is again an upper bound on performance with the support of our distribution, times the square root of D, the number of tunable parameters, times M, the number of constraints, times W squared, where W is the number of sequential cuts we're making at the root, times this log factor we saw before, divided by a capital N, where N is the size of our training set. So again, we're able to show this polynomial dependence on these key parameters in our tree search. So I'll finish up this section by describing how we can even generalize our guarantees beyond cut selection to other aspects of branch and cut. And to do so, let me just describe this kind of general model of tree search, where at every iteration, we're going to perform some T actions like node, variable, cutting, plane selection. And let's say that there are TJ possible actions of each type J. So like say TJ cuts in our cut pool, or TJ variables that we could branch on. And we're going to do this for a maximum of kappa iterations. And again, we're going to say that these actions are chosen using some mixture of scoring rules, as is commonly practiced in integer programming. And in this case, we get this generalization bound of H, where again, H is an upper bound on performance, times the square root of D. D is the total number of weights defining these weighted combinations of scoring rules, times kappa, the maximum number of iterations, times the sum of the log of the number of actions at each step. And this recovers a result of prior research, which studied only variable selection. And these are the first guarantees that handle these multiple critical aspects of branch and cut, like node, variable, and cut selection. Okay, so now I'm gonna move even beyond integer programming to describe a recent work by myself, Nina Balkin, Dan de Blasio, Travis Dick, Carl Kingsford, and Thomas Sandholm, which provides configuration guarantees for many other types of combinatorial problems beyond integer programming, but also including integer programming. So in this section, I'm going to describe a unifying structure that connects these seemingly disparate configuration problems, including clustering algorithm configuration, integer programming configuration, again, comp bio configuration, mechanism configuration from economics, and greedy algorithm configuration. And I'm going to show how the structure can be used to provide extremely general guarantees. So let's remember this key question we're trying to answer in this talk, which is fundamentally, if a configuration has good average empirical performance over a training set, can we guarantee it will also have good expected performance or good future performance? And in this very general model of algorithm configuration, performance can mean a lot of different things, like runtime, solution quality, memory usage, revenue and economic settings, and so on. And in this paper, we answer this question for any parameterized algorithm where its performance is a piecewise structured function of its parameters. So for example, it's piecewise constant, piecewise linear, piecewise polynomial, or piecewise something else. And we've already seen this structure in the context of integer programming. We saw that tree size was a piecewise constant function of these parameters. It turns out we see other piecewise structures in other contexts. So in the context of economic mechanism configuration, we've seen that revenue is a piecewise linear function of mechanism's tunable parameters. And in other configuration problems, we discovered other types of piecewise structure. So to give you an example, in a Cold 17 paper, we looked at clustering algorithm configuration, where this tunable parameters mu allow you to interpolate between classic clustering routines like single, complete, and average linkage. And we discovered that many different types of clustering objective functions, like say the k-means objective value of a clustering instance, is a piecewise constant function of these tunable parameters. So to talk about this piecewise structure a bit more formally, I'm going to fix a bit of notation. So let's say that RD is the set of all possible parameter settings, and X is the set of all algorithmic inputs. So for example, maybe X is a set of integer programs. And a little more formally, what do I mean by algorithmic performance? Well, I'm going to use the notation U mu of X to denote the utility of the algorithm parameterized by mu on the input X. So I'm going to use the terms utility and performance somewhat interchangeably. And again, you can think of this as runtime, solution quality, memory usage, and so on. Now, if I collect the set of all such functions U, I'll refer to this as the primal function class. And typically in learning theory, we prove these types of provable guarantees by understanding the intrinsic complexity of this primal class U, using notions like VC dimension, pseudo dimension, Rademacher complexity, and so on. But the challenge is that the set U is pretty gnarly. So for example, in integer programming, every element of its domain is an integer program. So it's unclear how to plot or even visualize these functions U mu. There are no obvious notions of smoothness or Lipschitz continuity that we can rely on. So this is where the notion of a dual function comes in handy. So rather than fix the parameter mu and vary the input x, we could just as well fix the input x and vary the parameter mu, and we get utility as a function of these parameters. And as you would hope, ux of mu equals u mu of x. And if I collect the set of all such functions ux, I'll denote it u star, and I'll refer to it as the dual function class. And then these dual functions are really nice because they have this simple Euclidean domain, RD. And they often have ample structure that we can use to bound the intrinsic complexity of the class we actually care about, U, the primal function class. So what I've been alluding to in this section is that across all these different domains, these dual functions UX are piecewise structured. They're piecewise constant, piecewise linear, or piecewise something else. And this piecewise structure is what unites these seemingly disparate problems from integer programming, clustering, comp bio, greedy algorithms, and mechanism configuration. And it's also been, this piecewise structure has also been used in the context of online algorithm configuration, which exploited some piecewise Lipschitz structure to provide regret bounds in that context. So now I'm just going to give a flavor of our main result because I'm starting to run low on time. So generalization, how do we prove these generalization bounds to future inputs? So I'll start with a picture. So let's say that we've got this two parameters, mu1 and mu2 along the x and y axis. In general, there can be any number of parameters, and we're plotting utility as a function of these parameters. So runtime, solution quality, and so on. And let's say that for any input, there are these functions f from some set f, which split the parameter space into regions, such that in any one region, the utility function equals some function g from the set g. So in this picture, g would be the set of all constant functions. So we prove that with high probability for any choice of this parameter setting mu, our generalization bound, the difference between average empirical utility and expected or future utility, is bounded by h, an upper bound on utility over the support of our distribution, times the square root of CF. CF is like the intrinsic complexity of the set F of boundary functions, plus CG. CG is the intrinsic complexity of the set G of piece functions divided by n, the size of our training set. And the cool thing is that we're able to recover the guarantees for integer programming and prove guarantees for many other domains using this very general input, very general theorem. And specifically for those of you familiar with learning theory, we prove the pseudo dimension of the set of all utility functions is bounded by the VC dimension of the dual of the set of piece boundary functions plus the pseudo dimension of the dual of the set of piece functions times log k, where k is the number of boundary functions. So overall, the main message of this section is that we're able to discover this unifying structure connecting all of these different configuration problems. And we're able to use this structure to provide these very general guarantees. Okay, so now I'm just going to wrap up with some conclusions. So in this talk, we discussed branch and cut, which is the most popular tool for solving combinatorial problems. And we provided the first guarantees for learning high-performing cuts and cut selection policies. We also saw how these guarantees can be generalized to this very general model of tree search, which handles these multiple critical aspects of branch and cut, like node selection, variable selection, and cut selection. Finally, we concluded with results that unify this diverse array of configuration problems like clustering, integer programming, computational biology, and greedy algorithm configuration. So with that, I'll wrap up and take any questions. Thank you.
Thank you very much, Ellen. Really great talk. So
Thank you.
Very excited to listen to this. Do we have any questions? Okay, so I have one hand. Let me see who is raising. Nathan, please go ahead.
Thanks, Ellen, for the informative talk. If I understood correctly, the bounds you presented are for arbitrary scores. I'm not really familiar with this space, but I wonder if there has been work on, like smartly learning more sophisticated scores.